Welcome all to the second lecture on module theory. In the first lecture we have discussed modules and submodules. Today we will discuss module homomorphisms. What is module homomorphism? So it is the definition is same as linear transformation, but in this case both domains and codomains these are modules. So we start with the definition of module homomorphism. Let R be a ring and M and N be two R modules. Then a map, set map phi from one module M to another module N, it is said to be an R module homomorphism or an R linear map if it respects the R module structures. So what I mean by that? So an R module, that means we have addition and scalar multiplication. So a set map from one module to another module, it is called an R module homomorphism if it respects both addition and scalar multiplication. In the sense that you consider two elements x and y, then you take their sum and you apply phi, then that is same as phi of x plus phi of y. So this sum it is happening inside M and this sum it is happening inside N, and same thing holds true for scalar multiplication as well. So it preserves scalar multiplication. So you take r times x and you apply phi, then that is same as r times phi of x. So this thing it is happening inside M and this scalar multiplication it is happening inside N. So all these together we can say that this is just equivalent to say that a set map it is called an R module homomorphism if it respects the R linear combination. That means r times x plus s times y, and you apply phi, that is same as r times phi of x plus s times phi of y, and this is true for all rs belongs to R and xy belongs to M. Okay, so that is the reason we say it R linear map. So this is categorical definition. So in case of group homomorphism, we just define it is a set map from one group to another which preserves the group structure. That means it respects that group operation. And what is ring homomorphism? It is a set map from one ring to another such that it respects both addition and multiplication in the ring. So in same way we define module homomorphism, and we also call it R linear map. Next we define what is module isomorphism. So an R module homomorphism phi from M to N, it is an isomorphism if there is an R module homomorphism psi from N to M, that means in the reverse direction from this codomain to the domain, such that their compositions are identity maps. So in some book it is defined that an R module homomorphism it is called an isomorphism if it is bijective as a set map, but we define in this way because this is the categorical definition. Categories. So for example, in the category of groups, how you define group isomorphism? So it is a group homomorphism such that you have a reverse group homomorphism such that their compositions are identity. In case of rings, in the category of rings, you define what is ring isomorphism. It is a ring homomorphism such that you can have a reverse ring homomorphism such that their compositions are identity maps. And what is isomorphism in the category of topological spaces? We call it homomorphism. What is that? It is special kind of continuous map such that you can have a reverse continuous map so that their compositions are identity. So this is the categorical definition we consider here. So if there is an isomorphism phi from M to N, then we write M is isomorphic to N, and we also denote in this way. So M to N and via this isomorphism symbol, and we call it M and N are isomorphic. So you consider an R module homomorphism, then canonically we can define two submodules. One is a submodule of the domain and another one is the submodule of the codomain. So we define in this way. So we call it kernel of phi, ker of phi, that is the collection of all those elements coming from the domain such that its image under this map phi, that is 0 element of N. So collection of all those elements coming from the domain whose image is 0 via this map. And second one, it is image of phi. So by definition, it is just collection of all the images of this map phi. So that means collection of all those elements in the codomain which is coming from the domain via this map phi. That means there exists x such that phi of x equal to y. So it is collection of all the images. Next we observe that if you start with an R module homomorphism, then the image of the 0 element of M, that is the 0 element of N. So how to prove this? Because we can use this property of 0 element. So 0 plus 0, it is 0. So you consider 0 element of M. So then you apply phi on that. Okay. So that is this one. And since phi it preserves addition, so phi of 0, I will just write 0, phi of 0, that is same as phi of 0. And from here you will get phi of 0, that is just 0 element of N. Now next thing is that kernel of phi, this is a submodule of M. And how to prove this? So from the first statement we see that 0 element, it is already there in kernel of phi, right? So this is a non-empty subset of M. And next thing, we want to use that submodule criteria. So we want to prove that this subset, it is closed under addition and scalar multiplication. Okay. So we will prove here. So this is the proof of the second statement. So you pick two elements coming from the kernel of phi, and R, S, both are scalars coming from R. So then we want to prove that R times X plus S times Y, this is also there in kernel of phi. So you just apply phi, and since phi preserves R linearity, so it is R times phi of X plus S times phi of Y, but both phi of X and phi of Y, these are 0 elements of N. So this is just 0. Yeah. So this proves the second statement. And the third statement, it says that image of phi, this is the submodule, this is a submodule of the codomain. So from the first statement, again we see that image of phi, this is a non-empty subset, because 0 element of N, it is there inside image of phi. Now only thing we need to prove that it is closed under addition and scalar multiplication. So this is proof of the third statement. So again you just pick two elements coming from the image of phi, and suppose R and S both are scalars coming from R. So then we just want to prove that R times Y1 plus S times Y2, this is there in the image of phi. So since Y1 and Y2 both are coming from image of phi, so there exists Xi in M such that phi of Xi, it is just Yi. And then you apply phi on this thing. Yeah. So yeah, then we want to prove that this element, it is there in the image of phi. So we can observe that this is same as the image of R times x1 plus S times x2. Yes. So this completes the proof of the third statement. So here are some properties of module homomorphisms. So let phi from M to N, this is an R module homomorphism. Then this phi, it is injective as a set map if and only if its kernel is trivial. Okay. And our second statement, it says that this phi, it is a module isomorphism if and only if phi is bijective as a set map. So let us prove this proposition. know that phi of 0 it is 0. Okay, so 0 element is already there inside kernel of phi, and if phi is injective, then any non-zero element it cannot map to this 0 element. So we have that kernel of phi it is just trivial singleton set consisting of 0 element of M. Now let us prove this reverse direction. So it seems that this is weaker conditions, but we are considering an R module homomorphism. So this weaker condition it forces that your map that should be injective. Okay. So this condition it says that in the kernel you can have only 0 element. Now let us prove this direction. So suppose phi of x it is same as phi of y. Now we want to prove that x equal to y. So from this equality we can have that phi of x minus y it is just 0 element, because phi it preserves addition and scalar multiplication. So it respects the R linear combination. Okay. Since kernel is trivial, so x minus y that should be 0 element, and this implies that x is same as y. Yeah. So this completes the proof of statement 1. Now second statement, it says that phi is a module isomorphism if and only phi is bijective as a set map. So if you recall the definition of module isomorphism, what is it? So it is just a module homomorphism such that you can have an inverse module homomorphism such that their compositions are identity maps. So in particular you have an inverse set map. So that means this direction it is trivial. So I should write this direction it is trivial. We just need to prove this direction. So we start with an R module homomorphism, and suppose that is bijective. Now we want to prove that it is a module isomorphism. Since phi is bijective, there exists an inverse set map. Let us say psi from n to m. An inverse set map, that is phi compose psi, it is identity map on n, and psi compose phi, this is identity map on m. So we just need to prove that this inverse set map it is actually a module homomorphism. Then we are done. So I leave it as exercise, that just verify that psi it is a module homomorphism. It is a module homomorphism, and you just need the fact that this phi it is a module homomorphism. So using that, and phi is bijective, you can prove that this inverse set map psi it is actually a module homomorphism, and then that proves that phi is a module isomorphism. Phi it is an R module homomorphism. Then this R module homomorphism it is called monomorphism if this phi is injective as a set map, and this is epimorphism if phi is surjective as a set map. And just now we have proved that this is isomorphism if phi is bijective as a set map. And we call a module homomorphism it is an endomorphism if both domain and codomains are same, and it is an automorphism if both domain and codomain are same, and also phi is an isomorphism. Okay. So these are the terminologies we want to use in this series of lectures. So here are some examples of module homomorphisms. When R is a field, then an R module homomorphism it is nothing but an R linear transformation. So how we define R linear transformation? So it is just a map from one vector space to another which preserves R linearity. That means it respects both addition and scalar multiplication. And definition of module homomorphism it is same, right? So in case of module homomorphism, only difference is that domain and codomain, it can be arbitrary module. When your base ring is a ring of integers, then what is a Z module homomorphism? So in particular, it is a Z module homomorphism. It is an abelian group homomorphism. But converse is also true, because the scalar multiplication we define in that way only. For example, 2 times x, it is just x plus x. So you consider your base ring is the ring of integers Z, and both the modules M and N both are same as R. So these are module over itself. So R you can think as module over itself. So which of the following are module homomorphisms among these two maps? So first one, it is defined in this way: phi of x, it is same as 2 times x, and for all x belongs to Z. So this map is defined in this way. Now is it a module homomorphism? So we can see that it preserves addition and scalar multiplication. So where scalars are coming from Z. So this is a module homomorphism, but I should note that it is not a ring homomorphism. Why? Because though it preserves addition, but it does not preserve multiplication, ring multiplication. Okay. So it is not a ring homomorphism, but it is a Z module homomorphism. What about the second map? So psi of x, it is defined to be x square. So we can see that it does not preserve addition. So it is not a module homomorphism even. So here are some more examples. So suppose M, that is the free module, free R module of rank n, and your n is same as R, that is free module of rank 1, free R module of rank 1. You consider n many scalars C1 up to Cn, and using these scalars you just define a map like this. So phi of these n tuples, it is same as C1 times A1 plus up to Cn times An. Is it a module homomorphism or module homomorphism? So we can verify that it preserves addition, where addition is defined component wise, and it also preserves scalar multiplication, where scalar multiplication it also defines it is also defined component wise. So this is a module homomorphism. So in particular, if you define pi j, that is just projection on the jth component. So it is defined like this, that you are mapping this n tuple to its jth component. Then this is just natural projection map, and since this is homomorphism, so directly we can verify that even this is also R module homomorphism. What about this one? So you define a map like this. So n tuples, you are sending it to A1 times A2. So is it a module homomorphism? So answer is no, that it is not a module homomorphism, because it does not preserve addition. Okay. So here are some notations. So you consider two R modules M and N, then you can define this set. So we denote it hom of M comma N, and what is this set? So it is just collection of all R module homomorphisms coming from M to N. Okay. And if both domain and codomain are same, so let us say M comma M, so hom of M comma M, so we give another name, it is just end of M, that means it is collection of all the endomorphisms from M to M. Okay. So collection of all automorphisms from M to itself, we just denote in this way, aut of M. So we can see that this is a subset of this one. Next we see that what structures we can give on these sets. Okay. So first one is that you consider hom of M comma N, then this proposition it says that hom of m comma n, it is always an abelian group. Okay. So abelian groups means we can have an operation, and with respect to that operation it is abelian group. And second statement it says that it is in fact an R module homomorphism if your base ring is commutative. So let us prove this proposition. So we want to prove our first statement. So you consider two module homomorphisms, phi and psi from M to N, and now we want to define an operation. So we define addition in this way, phi plus psi. So it is defined to be phi of x plus psi of x for all x belongs to M. So then you can verify that phi plus psi, first of all this is a map from M to N, and it preserves addition and scalar multiplications, because both phi and psi they preserve addition and scalar multiplication. So using that you can prove that this sum, this map, it preserves addition and scalar multiplication. So this is a module homomorphism. Now using this operation you can prove that this set it is actually an abelian group, because you can verify that this operation it is commutative and it is also associative, and we can have identity. What is that? So here you consider this map. So everything is going to 0 element of n. So this is for all x, and also each morphism phi it has additive inverse, namely minus phi. Okay. So this set it is an abelian group. The second statement it says that when your base ring is commutative, then you can have something more, that means it is R module. So in this case, the second statement, when your base ring is commutative, we want to prove that we can also define scalar multiplication in some way. So you pick a scalar from R, okay, and yeah, phi it is a module homomorphism from M to N, and this is module homomorphism. Then you define, so I should write, you define R times phi in this way by R phi of x, it is just R times phi of, so this is our definition, R times phi of x for all x belongs to M. So we are defining R times phi this map in this way. So R is a scalar coming from R and phi of x is an element of N. So this scalar multiplication it is happening inside N, and if you define in this way, then you can prove that this is a well defined map, and also you can verify that when your base ring is commutative, then this R times phi, again I will leave it as exercise, that verify R times phi is a module homomorphism if R is commutative. You need commutativity to prove that this map it is actually an R module homomorphism, and this gives the scalar multiplication, and you can verify all the other properties of scalar multiplication. So in particular this set hom of M comma N it is actually an R module, okay, when your base ring is commutative. Yeah, next we define algebra over a ring. So you start with a commutative ring with identity, and what is R algebra? So by definition it is a ring with identity element together with a ring homomorphism from R to A, such that the identity element of R it maps to identity elements of element of A, and also the subring, that is the image of this thing, it is contained in the center of A. So what I mean here, So an R algebra, it is nothing but it is combination of both the ring structure and module structure. So you can have an R algebra, it is by definition it is a ring together with this map, and we can prove that giving this ring homomorphism, it is equivalent to give an R module structure on A. Okay, so we can prove that you define, you pick something from R and something from A, then you want to define this scalar multiplication in this way. So via this map you just go to A, so that means you can consider f of R, and this is an element of A, and then you can multiply this by x. Okay, so this multiplication, it is happening inside A. So A is a ring, you can multiply these two elements of A, and your scalar multiplication you define in this way. So then you can verify that A is actually an R module. Okay, so I should write this gives a scalar multiplication. In fact, the converse is also true. So suppose you have an R module structure on A, then you can define a ring homomorphism like this. Okay, you can try it. And both the ring structure and module structure, both the structures are compatible in this sense, that f of R, it is contained in the center of A. So you can see what is the meaning of this statement in terms of this module structure. Okay, so summary is that an R algebra, it is nothing but a ring together with a module structure such that both the structures are compatible. So what is commutative algebra? So it is a commutative ring with identity together with a ring homomorphism like this, such that the identity element of R, it maps to identity element of A. So you don't need this condition when your ring A is commutative. Okay, because so what is center of A? It is just collection of all those elements of A which commute with all other elements of A. So if your ring is commutative, then everything is there in the center. Okay, so in that case you don't need this condition. So here are some examples of R algebra. So let R be a commutative ring, of course with identity. Then the polynomial ring in one variable over the ring R, it is an R algebra, because we can define a ring homomorphism where R is going to R, this constant polynomial. So this is a ring homomorphism, you can verify, and so here identity element of R, it goes to identity element of Rx, and f of R, it is contained in the center of this ring. Okay, so because you are considering commutative ring, so this polynomial ring, it is an R algebra. Another example, so you consider an ideal I of R, then the quotient ring R mod I. So this is also an example of R algebra, because you can define a map like this. So you can have this natural projection map. So R goes to R bar, and it maps identity element of R, it goes to identity element of R mod I, and of course you are working in a commutative ring. Okay, so R mod I, it is an R algebra. So here is something non-trivial R algebra. So you consider an R module, let's say it is M, then we have we have seen that phi plus psi, that sum you can define, and that is again an R module homomorphism from M2 itself. So if you consider two endomorphisms phi and psi, then you can take their sum, and that is also an endomorphism. And this one, it is just composition map. Okay, so you can verify that if both phi and psi are endomorphisms, that means module homomorphisms from M2 itself, then their composition is also so. Okay, so using these two operations, so with these operations as addition and multiplication respectively, this set that is collection of all the endomorphisms from M2 itself, this is actually a ring. You can verify all the properties of ring. So here addition is defined in this way and multiplication it is defined in this way. Okay, so of course it is not a commutative ring. Okay, but you can have identity element which is just identity map from M2 itself. Moreover, if your base ring is commutative, then this is this endomorphism end of M, it is actually an R algebra. Okay, so let us write something to prove this statement. Define a map from R to this ring as follows. So you consider an element of R, then we map it to mu R. And what is mu R? It is, this is a map from M2 itself defined by multiplication by R. So you can verify that this mu R, it is actually an R module homomorphism from M2 itself. So this is an endomorphism. And then if you map R to mu R, then this map, it is actually a ring homomorphism. So this is exercise that F is a ring homomorphism. So you can verify that it preserves both addition and multiplication. So f of R times S, it is just mu of Rs, and this is same as mu of R compose mu of S. So this is same as f of R times f of S. Okay, and also it maps the identity element of R, it is just mu 1, and this is identity element of endomorphism of end of M. Okay, and of course you can verify that image of R via this map, it is there in the center of this ring, because mu R, it commutes with each element of end of M. So mu R, it is there in the center of this ring, and it proves that this end of M, it is actually an R algebra when your base ring R is commutative.